Okay, thank you so much. Good morning, everyone. I'd like to thank the organizers for giving me this opportunity to talk today about the work I've been doing in the past couple of years with Simon, Joel Geet, Anosh, David Sheikh, and Toby Wiseman. So I'll mention some results from lattice supersymmetry simulations in 2 dimensions and 3 dimensions. As you can see, the title itself is very safe. I'll not talk about the 4 dimensions. So that's why I'll focus entirely on 2 and 3 dimensions. As we all know, there are certain problems, and work is ongoing to understand n equal to 4 superangles in 4 dimensions. So I'll not talk about anything in 4 dimensions. We'll hear more about 4 dimensions in the next talk, so I'll just focus on lower dimension for the time being. So let me outline the talk here. I'll start with motivations of doing lattice supersymmetry, and then I'll talk about what are the possible theories which we can target with our construction in several dimensions. Moving on, I'll discuss the 2-dimensional 4 supercharged superangles, which you have heard a lot about from the lectures given by Simon in the past 3 days. And I'll talk about the supersymmetry breaking in that theory. Moving on to one higher dimension, I'll talk about the holographic connection, which we can do via studying 3-dimensional superangles, which is the 16 supercharged superangles in 3 dimensions, maximal supersymmetric angles in 3 dimensions. So that will be the basic flow of this talk. So first of all, let me motivate. We have already heard a lot about this in the talks given, but let me just say, why do we want to do supersymmetry on the lattice? As we know that lattice provides a natural discretization and gauge invariant regularization of gauge theories, and it provides a possible non-perturbative analysis of various things which we want to do. More importantly, gauge gravity duality is accessible if we can understand the strong coupling regime of supersymmetric gauge theories, and lattice is a very natural choice in this context. On the lattice, we can not only do the large planar limit, but we can also do some finite n calculations and see how it matches with the 1 by n or 1 by n squared corrections. Lattice supersymmetric theories are a good playground for studying confinements, phase transitions, symmetry breaking, and obviously in 4-dimension n equal to 4 famous conformal field theories. So this is the basic motivation we have for studying lattice supersymmetry. So the initial studies of lattice supersymmetry started back in the early 80s, but there were certain problems which people encountered immediately. The problems are related to the algebra, supersymmetric algebra. So supersymmetric algebra extends the Poincare symmetry by adding these spinorial generators, Q and Q bar. And just looking at the supersymmetric algebra, we see that they generate infinitesimal translations, P mu. And these P mu are broken on the lattice, so that means the supersymmetry is explicitly broken at the classical level, and there has to be a different way of trying to put supersymmetry on the lattice. The solution which has been proposed in the last decade or so is that let's aim to preserve some subset of the SUSY algebra. For example, if we start with a certain number of supercharges in the continuum, we'll try to preserve some of the supercharges exactly on the lattice, and then hope that we get back the remaining supercharges when we take the continuum limit by doing some kind of fine-tuning. So these kind of methods are based on orbifold construction and topological twisting. And these have been shown that they give identical results, and they are shown to be equivalent. In this talk, I'll just focus on the latter construction, which is the topological twisting. So let's see what lattices we can access by this construction in various dimensions. In 2 dimensions, you can do 4 supercharge, 8 supercharge, and 16 supercharge. All 3 of them are possible. In 3 dimension, you can only do 8 supercharge and 16 supercharge. In 4, n equal to 4 superangles is the only example which we can do on the lattice. The reason this is true is because this prescription of keeping an exact supercharge on the lattice is related to the content of the continuum theory. So What we need is we should have sufficient number of supersymmetries in the continuum, and then we preserve some subset of that. So for example, that goes as 2 to the power d. So you should at least have 2 to the power d supercharges in the continuum so that we can write do a twisted lattice construction of that and do simulations. So that means in 4 dimensions, 16 supercharges is the only exception to this rule. But the important thing to note here is that in all the dimensions, the 16 supercharge theory is accessible on the lattice. As you can see, in 2 dimensions, 3 dimensions, and 4 dimensions, all the 16 supercharges are possible to study on the lattice non-perturbatively. And that is a good thing because we want to study, if we want to study gauge gravity duality, that's where the duality is, maximal supersymmetric, 16 supercharges. So it's possible in all the dimensions. So starting with n equal to 2, 2 superangles in 2 dimensions, we can write the action in a Q exact form. So we can write the action as Q acting on something, and that something is given by this quantity. Lambda is given by trace of chi AAB, FAB. I'll show you in the next slide how these Q transformations act on various things. But this is how I can write down the n equal to 2, 2 superangles action in a Q exact form, where lambda given by G square n is the Thoopt coupling. The nilpotent supersymmetry transformation, which we heard about from lectures given by Simon, can be exposed in this theory. We can have the scalar supercharge Q, which is Q square is sums to 0, and that can be seen by just looking at Q acting on A gives me psi, and Q on psi is 0, and you can see clearly that Q squared is 0. So there's a nilpotent supersymmetric transformation, basically a 0 form, or basically equivalent to a site fermion, which you can hope to exactly preserve on the lattices. It has no indices, 0 form. So that's the supersymmetric transformations we have with this Q scalar supercharge. So as you can see that it turns a boson into a fermion and so on. Q acting on chi AB gives me a minus FAB, and that just gives me, if I act on Q on this lambda, I just get the kinetic term and so on. So these are the supersymmetric transformations we have. So there are 4 degrees of freedom in this theory, and we can break that into a 0 form, 1 form, and 2 forms. So eta, psi, and chi. I have one eta, there's 1 0 form, 2 1 forms, and 1 2 form, giving me the 4 degrees of freedom. We construct a complexified field from the usual gauge field and 2 scalars in the untwisted theory, as we have seen already, that we combine them together and make this calligraphic A's construction, which has the gauge fields and a scalar in them. And we write this complexified covariant derivatives in terms of these calligraphic A's and A bars. And in this case, the complexified field strengths can just be written as the dA and D commutator of dA, dB, and so on. So this is the natural prescription of the twisted theory which we have. The action can be split up in 2 parts, bosonic action and the fermionic action. And it can be written by SB written like this, where this is the coupling and 1 over 2 lambda, and this we have the trace of this part, F bar, F part, and this kinetic part, and then we have the fermionic piece. Another term which we add to our action is the mass term, which breaks Q supersymmetry. We need to add this term to control the flat directions. So what we do is we add this term to the action, which goes as mu square times, it pushes the link towards the, this makes it possible for the links to have the desired continuum property which we want to access the continuum theory. We add this term, and what we do is we do the simulation for various values of mu and then take the extrapolation in mu squared to 0. And then what we have at the end is an exact theory which has Q supersymmetry intact. So we remove this breaking term by taking extrapolation in mu squared. How do we do these fields on the lattice? So that's pretty straightforward. We have a square lattice in 2 dimensions. You have this, I said that there is a 0 form site fermion, which is this eta, and then you have psi 1 and psi 2. And then you have a chi 2 form chi AB, which runs opposite to the kind of body diagonal. So this chi AB goes from n plus mu1, mu2 to back to n. And these give me the 4 degrees of freedom which I want for this theory. As you can see, that calligraphic U's and psi both live on links in this case. So we have 4 supercharged, and this is the way we organize them on the lattice. So I mentioned that we do certain extrapolations. So for example, when we are trying to understand the supersymmetry breaking in this theory, the first thing we have to do is we have to start with the extrapolation in Q square. So this is the term which breaks Q supersymmetry softly. So we extrapolate in that term on various lattices, and then we do a continuum extrapolation for various values of this deforming parameter. And then at the end, we do extrapolation in temperature. So we want a 0 temperature limit. We want to understand whether the supersymmetry is broken or unbroken when you have a 0 temperature. Now, I might as well have done with periodic boundary condition, but it turns out that there are certain complications. So we do our simulations with anti-periodic boundary conditions on the fermion along the time cycle, and then do it for various values of beta. So this beta here also defines the coupling. So when I go to very low temperatures, I'm basically going to very strong couplings. So I start from weakly coupled theory and then go to large values of beta and then see whether this is consistent with 0 or not. As you can see in this plot very clearly, it starts off from some high positive value at small values of beta, and then as I take the beta going to beta going to infinity limit, I get something which is very close to 0. So I'm zooming in on this part in this inset. And as you can see, we have tried to do very big lattices up to 96 square on different values of masses. And even by doing that, we couldn't be completely sure whether there's a very small 0 vacuum energy or is it a non-zero energy. So as we can see that the extrapolation, because this strong couplings correspond to very low temperatures, and it seems that the energy is indeed consistent with 0. Sorry? Yes. So this is true, but yes, exactly. And the reason these points at, for example, 6 and 7 are consistent with 0, and then you have a positive value. So we are not very sure about how to do this. This is very delicate business in the sense that whether it's, yes. So
I meant if center value distribute, positive side and the negative side, I would say it's consistent with 0, but it always.
Yes, certainly. I agree. Yeah. So let's see. The prescription is to calculate the ground state energy density in the limit beta going to infinity. We need to use small mass term mu to control flat direction, which we extrapolate to 0 after doing the continuum extrapolation. So you can first do the continuum extrapolation and then do the massless limit, or vice versa. The difference is not very substantial. So we think that the upper bound on the energy density is this number, which I write here, 0.052, but this has no temperature dependence in it. So basically this is the maximum value which you can have possibly, which we see on the lattice. This is not the first time this has been explored on the lattice for this theory. This earlier study was done by Kanamori, Sugino, and Suzuki, which was based on an alternative twist of this theory. So as we heard in the lectures, there are 2 possible twists of this n equal to 2, 2, A twist and B twist. I think this name goes back to Witten. And this is based on how you embed the R symmetry group in the twisted rotation group. So this theory has certain R symmetry group, and depending on what subset of R symmetry you want to embed in the twisted rotation group, you can have different kind of twists. So we are working with B twist, and sorry. So we did numerical simulations for n equal to 2 and n equal to 3. What I'm showing you is for n equal to 3. Yes, in the paper we also have n equal to 2 results. Yes.
Similar conclusion?
Yes, similar conclusion, exactly. So it seems that whatever is happening is kind of an independent. Breaking or unbreak, yes. Okay, so that was the story I had in 2 dimensions where I discussed about the supersymmetry breaking in this theory. Moving on, Let me now talk about the applications to holography or gauge gravity duality, because this is something which I'll talk about in 3 dimensions. So the original ADS-CFT correspondence related the n equal to 4 superangles, which is associated with the world volume of ND3-branes, is dual to type 2b on some geometry which is NT de Sitter 5 cross 5 sphere in the large n limit. So this is the original ADS-CFT correspondence. But just a year after this ADS-CFT correspondence, Marlesina and other people generalized this idea to lower dimensions as well. So not only we cannot only talk about gauge gravity duality when the field theory is in 4 dimensions, but we can also talk about the holographic principle or gauge gravity duality in lower dimensions. And we have already heard a lot of talk about the case where P is equal to 0. So if I put P equal to 0, it's a quantum mechanics case, matrix model, and we can study holography in that theory as well. But that is true for any value of P, P 0, 1, 2, and so on. So the more general holographic dualities say that at low temperatures and in the decoupling limit, this decoupling limit is interesting to understand, but it can be thought of. So when I say ADS S5 cross S5, what is happening is the bulk is getting decoupled from the world volume, and these are, so you have 2 parts. So you have a 10-dimensional geometry which is breaking up into ADS S5 cross S5, and similarly in low dimensions, when what we get is in the decoupling limit, the bulk decouples, and the theory you're left with is the supersymmetric theory. So this decoupling limit is very important in the sense that this also tells us that n has to be infinity, and the dimensionless temperature, which we construct as this. Remember that 't coupling in lower dimensions is dimension pool, so you can construct this dimensionless temperature depending on T, has to be kept very less, much less than 1. And that is the regime in which they said that this gauge gravity duality should be valid. So let's talk about maximal supersymmetric angles for P less than 3. Since P is equal to 3 is the 4-dimensional case, I won't talk about that. I just focus on the lower values of P, lower dimensional theory. So what we do is start with the n equal to 4 superangles and reduce that theory along 3 minus P spatial directions. So if you want to study, for example, 3-dimensional theory, I reduce it along 1 spatial direction. And that corresponds to doing a dimensional reduction. And that gives us a lattice which goes from A4 star to AP plus 1 star. So basically A4 star to A3 star and A2 star and so on. The important thing about this A4 star lattice construction and its lower dimensional analogs is that the basis vectors are not perpendicular to each other. The basis vectors are not 90 degrees, and there is some kind of skewness associated with this geometry. And that can be just written in terms of P as this. So for example, in 2 dimension, I have gamma equal to minus 1 by 2. That means cos theta is 120. That means you have 30 degrees off from being what would have been orthogonal basis vectors. 't coupling is dimensionful in P less than 3 dimensions, and we construct a dimensional coupling like this. In 1 dimension, there is no phase transition, at least in the BFSS model. I'm not talking about the BM model. At least in the 16 supercharged non-deformed model, there's no phase transition in 1-dimensional quantum mechanics. But the structure is richer for 1 and 2 dimensions. Because in 1 dimension, you can have certain transition between the uniform black string and localized black hole and so on. So what is the region where the supergravity description is valid? To have a valid supergravity description, or SUGRA, the radius of curvature should be very large in units of alpha prime. This implies that R effective should be much greater than 1. And R effective is just the quantity written here. So basically, this just means that the temperature should be very small. The string coupling should be small, and that corresponds to the fact that G Yang-Mills should be going to 0 as I take a strong coupling limit, and that means N has to be kept very large. I can combine these constants and get something like this. So the effective dimensionless coupling should be greater than 1, but it should be less than n raised to the sum power of this. So if I just put P equal to 3 here, I see that this just gives me n. And that is the usual 't limit. You keep lambda strong, but you make sure that n goes to infinity faster than lambda. So this is analogous to what we have in the lower dimensions. And this is the condition which we have to follow at each time if you want to probe the correct supergravity description. So let's go through a progress report through various dimensions, what work has been done. So for example, p equal to 0, the first work, I'm just mentioning the work which started. So there has been a lot of work over the 10 years. I'm just saying that the first work was started back in 2007 by Masanori, Nishimura, and Takeuchi in this paper, and also by Simon and Toby in a paper which came out in the same month, actually. So these two papers started the p equal to 0 studies, and then for p equal to 1, we have done some work in the last year for p equal to 1, and you'll see talks by David Shake and Daisuke Kado, which talk about this p equal to 1 case. What I'll do in this talk is I'll talk about p equal to 2, preliminary work we have been doing, and show you some results from that. There's a big dot here because what is the eventual goal, as Masanori pointed out, is to understand the thermodynamics of the n equal to 4 superangles. N equal to 4 superangles have some temperature behavior at strong and weak coupling. So basically it amounts, the simplification of the problem can be stated like this. Can we understand there is some function f lambda such that f0 is 1 and f lambda is 3/4? So there is some function that multiplies the T4 dependence, which is 1 at for the free theory, 0 coupling, and is 3/4 at infinite coupling. So the eventual goal, maybe after 4 or 5 years, is to get to understand that. But that is something which is not very clear to do, how to do right now. So I'll move directly to p equal to 2 dimensions, maximal supersymmetric in 2 plus 1. So I just write down the regime where we have the perturbative super Yang-Mills, and then we have a D2-brane description, and then as you go to very low energies, you have a different description in terms of uplifted D2-brane, and then as you go to very small temperature, you flow to this n equal to 8 superconformal field theory. So this from the very famous Magu review, Physical Reports by Aharoni and Nalesina. They have this plot, and they talk about all the non-conformal. So this is a very nice report to read, and you can see that what I want to focus is between this 2A D2-brane. So it's simple to write this in terms of the numbers which we use, and it just says that, okay, so I have to use effective dimensionless coupling, which should be greater than 1, but should be less than this power of n. So n to the power 6 by 5, it should be less than that. So for example, if you keep on increasing n, you have more window where you can do these kind of analyze this region. So you need sufficiently large n, and then if you are restricted to this regime, you can study the thermodynamics of the dual 2A D2-brane. Okay, so we have already heard a lot about this divergence of the thermal partition function that is prominent in this low dimensional theories. So this work was actually initiated back in '88 by a paper by David Nicolai. The paper, it talks about supermembranes, but it was also continued later on in '99 by Kabat, Lifshitz, and Lau. When they talked about this divergence of the thermal partition function, it was also shown very, like in 2009 by Simon and Toby, that what is happening is you can write the, for example, you can write the free energy as some constant times n log of some parameter, which is a regulator, IR regulator, and then you have the n square I finite part. So as you can see, the divergence which is associated with this part here is a 1 by n effect. And even Hawking radiation is a 1 by effect. So there has been some ideas about how this term might be related to the radiation and so on. So this is telling me right away that if I consider n to be very large, this term will keep on increasing and this effect will eventually go off. So this is another need for large n, which is not just because of the holographic principle or gauge gravity duality. It is something which we see practically in our simulations, that we large n to control the instabilities or the divergence which is related to the thermal partition function. So so technically speaking, we cannot do very large values of n in 3 dimensions at least. So what we need to do is we need to use some kind of a regulator and then try to see how this thing is changing as I vary the regulator. So that will amount to adding a mass term, which I showed you before for the 4 supercharge case. So I add a term, a potential to the action similar to that term, and we'll see what are the effects as I take that term to 0. Yes?
Do I understand it correctly? The n squared is because we have, it's a theory with adjoint, so we have n squared degrees of freedom. That's natural.
Goes as n squared. The leading behavior goes as n.
Right. I'm not familiar with that, so it's a naive question. How do I get n in a theory with adjoints where everything runs in powers of n squared?
Oh, for this thing, because this is related to the scalars and so on. So it's like a...
But they're also in the adjoint.
They're also in the adjoint, but I think there's some term which suppresses this contribution by 1 by n. So you have n squared going with the both.
Okay, maybe we should discuss it later, but I think that in a theory with adjoints, which is dual to a closed string theory, everything runs in power of 1 over n squared.
Yeah, but this is not a content.
Right, so that's 1 over n squared. Okay.
Sorry? Yeah.
It's the cartan.
Yes. Xi, xj, basically. So think of this as xi, xj, not xi, xj square. Xi, xj, basically, yeah. Okay, so let's use some mass term in our simulations and then see what is happening. So this is the dual thermodynamics of D2-branes. We can see the prediction which we have. So the prediction should go as this, 2.492 n squared lambda 3t 10 to the 10 by 3 for p equal to 2 case. This is all given in this paper by Harmak and Obers and Izaki, which introduced this. So we do a lattice simulation and confine ourselves to the uniform D2 phase, choose very low temperatures, large n.
In the previous slide,
Yes.
the factor of t you get, t to the power 10 by 3,
Yes.
do you get from simulation or you just put it by hand?
This is the prediction from the supergravity analysis, that this should go like this.
Oh, okay.
So this is the analysis done by people on the...
Okay.
And that's the prediction.
Okay.
Okay, let's move on. So computational cost goes as n to the power 7 by 2, so we cannot do ideally very large values of n. So what I'll do is I'll restrict to n maximum of 8, and on several lattices I use a small mass regulator, which I discussed before, which acts like this term in the free energy, and then take this to 0. This code is available on GitHub, and you can do study these kind of theories on that. So let's see. Let me start with 3 different values of zeta and see how it looks. So the dash curve here is what you want to get to. This is the supergravity prediction. If I use a mass term which is very large, and I calculate this energy density, I get something like this. Terribly off. There's no relation to supergravity. Let's use a small value of mass term. I get back here. Even smaller value of mass term, 0.10, I get here. And if I go to the 0 limit, I get something like this. And this is the preliminary plot I have, where I have this, all the points are extrapolated to 0. So I use a IR term which controls the divergence, and then send that term to 0. The prescription in which some term is to be sent to 0 is not very well known. So we just do a linear extrapolation in zeta square, and then read off the value of energy density. And this is what we get. I have plots from 2 different values of n and 2 different lattices. So n equal to 4 and n equal to 6 right now, and on 8 to the 3 lattice and 12 to the 3 lattice. I remind you that these lattices are chosen such that you end up in a uniform D2 phase. You can have different phases in this theory, and based on the ratio between the spatial extent and the time direction, you can end up in different regions of the phase space. So this ensures that I'm in the uniform D2 phase. It should be the D2 prediction which we have. So this is the preliminary results. So we have to go to bigger values of n. We can go to n equal to 8 and 10 on bigger lattices, probably not bigger than 12 to the cube. We try to do some lattices, and the preliminary results are very consistent with the predictions which we accept. So I remind you that this dashed red curve is the large N strong coupling. There are no corrections to this whatever. This is the leading supergravity behavior. And we are just trying to see where our simulations are taking us on that curve. There are certain other things which we can do in this 3-dimensional maximal supersymmetry. We can understand the quark anti-quark potential. This famous paper by Maldacena has a prediction for the potential between these. And written in R variables, this goes as alpha RT 1/3 by L, where alpha is the ratio between the spatial and the temporal size. This has to be only calculated when the size of the Wilson loop is very big, corresponding to that it is not entirely perturbative regime, it's strong coupling. So yeah, thank you. I'd like to thank my professor.
Of questions?
So I have two short questions about the three-dimensional case. First, what about fine-tuning? You don't need it. So probably you are not doing fine-tuning at this moment. And
I'm not doing anything. I'm just saying that I just take a 16 supercharge theory on the lattice which we have. I don't know anything about fine-tuning. I just calculate the free energy and see where it takes me on the supergravity curve.
So in principle, in continuum limit, do you expect you need a fine-tuning or not?
In this theory, it should be fine. That's why I'm saying 4-dimension, we are not sure. But in this theory, we have 2 supercharges exactly on the lattice. So the 4-dimensional theory has 1 supercharge. When you dimensionally reduce, you get another side fermion, which corresponds to an extra Q. So we have 2 Qs.
So I remember a long time ago, Mita Tunzao said for 3-dimensional maximal supersymmetric theory, probably fine-tuning is not needed. But he, at the same time, he said he didn't publish that result. So I'm not sure if it's established.
Yes, that's an open thing. I know. I think that, but looking like the from the simulation result, I think in 3D it should be fine. Yep.
So in the IR, the 3D super Yang-Mills, maximal super Yang-Mills is supposed to flow to the M2 brane, which is, I think, one of the other canonical examples of ADS-CFT.
Yes.
And that's now known to be described by superconformal Chern-Simons theory.
Yes.
So what are the prospects, I guess, of, I mean, okay, probably it's difficult at this stage to access that numerically.
The problem is that there has to be a proper prescription or proper understanding of, so the problem is that region which you are talking about becomes accessible at very small temperatures. And with the N which we run at, or for example, the N we study, it's almost impossible to go to that region. So you can go to that region with using a very big mass term, but we are not sure how much it will deform the theory that you are actually doing the physics, which is the physics in that regime. So you have to be at, once you are at sufficiently large N, or you understand how to regulate these divergences properly, then you can go to very low temperatures. So if I just see in this plot, let's look at this plot. So the T which we go to is T of 0.3 something. And that also has to be done by taking 3 different values of regulator and doing the extrapolation. Going further down, you just cannot do it at this values of N. That's my...
And what are the prospects of formulating Chern-Simons theories on a lattice, twisting them and so on?
Yeah, Chern-Simons, we all know about the problems related to that, but yeah, I don't want to...
Chern-Simons lattice is very difficult.
It's
So probably people don't think by using currently available method, we can define ABGM theory directly on lattice.
Mm-hmm.
But so we know how to define 3-dimensional YAMLs. So in principle, if by going to very strong coupling, it flows to ABGM. So it's in practice problem, and in principle it's okay, I think.
Yeah.
And directly defining ABGM is very difficult because we don't know how to treat the Chern-Simons term properly, probably.
Maybe one more question at most.